We are all very familiar with the slinky and have probably realized its many interesting properties. My lab analyzes a very interesting characteristic of the slinky, the way it falls. Let's take a look at this analysis from Tracker. Mass A represents the bottom of the slinky, while mass B represents the top of the slinky. In the slow motion video, we can clearly see that the bottom of the slinky stays stationary until the top of the slinky reaches it, at which point the whole slinky falls downwards. We can see this finding represented in the plots of y position of the top and bottom of the slinky as well. The bottom of the slinky remains at a constant y position and goes through a minor oscillation just prior to its fall. Comparing both plots on the same graph, we see that the top of the slinky falls until it reaches the bottom of the slinky, at which point the entire slinky falls as a single mass with gravitational acceleration. Note that the top of the slinky falls at a linear rate. This is due to interactions between adjacent coils of the slinky. Here's a brief explanation of the phenomenon. The bottom of the slinky will only fall once the tension on it changes, but from the moment the top is released, the change in tension propagates down in a wave-like manner to the bottom of the slinky, taking time. Meanwhile, the bottom of the slinky is held by the tension of the rest of the slinky, until the top reaches the bottom and the mass falls with gravitational acceleration. How might we go about analyzing the slinky further? The modeling of the slinky is quite complicated, and many research papers have been written on the topic. And their models use very high-level math, which I must confess to not understanding. I am using a simplified version of the model by Alan B. Downey, who gives us a way to model the velocity of the top of the slinky. Because his model is simplified, it does not model the falling slinky properly. However, we are specifically using only one fact from there, computation of the net speed of the slinky top. For that specific purpose, his model is fine. To model it, we can construct the slinky as the composition of many different springs joined together, each with only one coil, so they can compress independently of each other as the entire spring collapses. The segments, the smaller springs composing the bigger slinky in the model, will be shown in red and black. Let's go through the code. In the beginning, I've defined a class parameters, which lets me access different quantities when I want to. Here we set up the display window along with the velocity wave speed. Here we model the equilibrium position of the slinky when it is stretched by gravity. Each of the segments of the slinky stretches by different lengths, and this is the ratio in which that occurs. Here we model the motion of the falling slinky with wave speed, the linear speed of the top of the slinky. Please do look at the code in more detail, try to run it, and also visit Alan B. Downey's site, provided in the second set of comments in the code. This was my second attempt at modeling the situation. Earlier, even though the mathematics is difficult, I figured I could construct an iterative VPython model in which small motions are analyzed using spring forces. I tried to put such a model together, but failed. Upon further reading, I believe that the reason my attempt failed is because much more detailed analysis of the collisions between spring coils is required. It is not clear what parameters can be used to model these collisions. But for now, this model works well. Now let's run the code and see what it does. The model looks good. Thanks for watching.